be talking about Argonne Lab a little bit, just to give you a feel for it. Why we decided a few years ago to have a training program like this one, and some details about the curriculum, and then a bunch of logistics to orient you to how things are going to work out this next couple of weeks. Well, some of you may know this, but in my experience, not everyone is aware that the Department of Energy has a big set of national laboratories, as they're called. And so this shows where many of them are. We're here, of course, and Argonne happens to be the first national laboratory ever. Now you might say, well, what about Los Alamos? That was started in the early 1940s, in Argonne in 1946. Well, Los Alamos started as a national scientific laboratory, not a national laboratory, and later it changed. Small difference. Any case, there are a lot of labs. Some are well known, like Stanford Linear Accelerator, but others maybe not as much. Thomas Jefferson National Accelerator Facility. So the Department of Energy funds a lot of basic research as well as applied research. Now, Argonne got started basically, you could think of it as December 2nd of 1942, the first controlled nuclear fission reaction, which took place under the stands of Stagg Field at the University of Chicago, when the University of Chicago had a football team. And the stadium is no longer there. But this is a drawing that shows people led by Enrico Fermi and others doing the first controlled reaction. And these are little graphite blocks. Now, today, Argonne has branched out. It started out based on Enrico Fermi's idea after the war that atomic power could be used to produce electricity, so peaceful uses of the atom. And we still do a lot of work in that area, but in addition, there's a lot of work on energy science, battery design, for example, materials for batteries. The Chevy Volt automobile, which has batteries in it, those batteries were designed at Argonne years ago and under license to General Motors. They're now in the Volt. And there's a lot of work on research for better batteries. And in fact, on Tuesday night, if I remember correctly, George Crabtree, who heads a very large project at Argonne, will be talking about research in that area. We also deal with environmental sustainability, still do the nuclear national security. And then there are user facilities, which are shown more here. The Advanced Photon Source is one of the brightest X-ray sources in the world. I think it is the brightest one in the Western Hemisphere. There's the Argonne Tandem Linear Accelerator System in the Physics Division, Center for Nanoscale Materials, Electron Microscopy Center. And one of the user facilities is MIRA, our leadership computing computer. So to me, that shows how far along computational science and engineering have come, in that it's an international user facility, just like accelerators are. Now, 20 years ago, people would not have thought of it that way. You say, well, a computer is something you use when you have to. Now it's a major research facility that people from all over the world compete to get time on, just as they do to get time on these other facilities. Argonne has been active in computing from the very early days. Of course, in the late 40s, people were just using calculators. Even then, by the way, it was parallel computing, because Enrico Fermi and others quickly figured out that you wanted to have a room full of people, a room not too different from this one, in fact, but in those days, no air conditioning, with a calculator. And so they were given parts of the work to be done, including then passing on their results to somebody else. So it was parallel computing way back then. But of course, as soon as real computers started getting built, Argonne got interested in that. They found out that John von Neumann had designed one at Princeton, and decided to, and asked could they have the preliminary design, which they did, and then they built one So it was called AVADAC, Argonne's version of the institute. That's the Institute for Advanced Studies at Princeton, Digital Arithmetic Computer. And it actually was built and was working before Princeton got its own working. And so in the press release, they say, well, it's 100,000 times as fast as a trained computer, because that used to be a job title, using a desk calculator. And Oak Ridge found out about it and said, can you help us build our own computer? And so Argonne did, and it was called Oracle. So it was built at Argonne, then moved to Oak Ridge. This gives you a feel for part of the campus. It's a fairly large campus. So the advanced photon source is here. The leadership computing facility is in this building with a name that I like, Theory and Computing Sciences. And then building 208, which is right around here, there, is where the nuclear energy exhibit is. So why did we decide to do the Argonne training program for extreme scale computing? Which is a pretty cumbersome title, isn't it? And why extreme scale? Well, extreme scale because the next step in high-end computing is known as exascale. Right now, it's petascale, so it's 10 to the 15th floating point operations per second. Exascale is 10 to the 18th. But we didn't want to stick to just one particular milepost on the way to Yotta scale, for example. So we'll just call it extreme scale. It's a training program. It's not a school, although you might think of it as a summer school. There's a reason for that as well, which is that the National Science Foundation is supposed to do education and not the Department of Energy. And so to avoid pesky issues with Congress saying DOE shouldn't be having schools, I know it's silly, but that's the way it goes. It's a training program. The idea is, people who do computational science and engineering, as all of you do, and I hope will continue doing for much, if not all of your career, you have tools, these computers that are getting faster, not because any one processor is getting faster. They've been about the same speed since 2004. They're getting faster because they have a more complex architecture within each core, and we just have a lot more cores or GPUs. So it makes things more complicated to implement your models. And furthermore, because these are so powerful and they have so much memory and I/O speed, you're able to tackle problems that are themselves much more complex. You don't do just climate modeling the atmosphere and the oceans, but you also model the forestation on land and the topography of the land and clouds and ice sheets and glaciers. And you want those all to be part of one simulation, as an example. That's pretty complex to do. Different time scales, different spatial scales, and many different phenomena. So that's what I mean by the applications are themselves complex and getting more complex. And so already when you're in graduate school, those of you who still are, and those of you who are out of it, you had to take a lot of courses, learn a lot of things, but typically we're not given the opportunity to learn about other things that you still need. So one example I usually give is software engineering. Did any of you take courses in software engineering as part of your PhD? I see 3 or 4. Excellent. But that's a pretty small percentage. And yet, chances are you'll be working as part of a team that's developing a big complex code, and so you have to worry about the engineering of the code when many people are working on it, updating it, adding new capability, new functionality. So that becomes very important. Visualization is often the only way that you can figure out what happened in your simulation. And so you don't have to become a visualization expert yourself, but it's good for you to be exposed a little bit, as you will be next week, on Wednesday next week, to visualization tools that are available for highly parallel systems. So that's the kind of specialization that I'm talking about. Now, in 2 weeks, we can't cover everything in big depth. I wish we could. when I first started thinking about this program, I thought 6 weeks was about right. But, and so you're going to do 6 weeks worth of work in 2 weeks, right? But I decided quickly that it's not likely that very many of you would be able to take that much time off, plus the funding would be a little bit of an issue. So what we were going to do is expose you in some depth on various topics. For example, the next, let's see, the Tuesday, Wednesday, Thursday, go into a lot of depth on advanced MPI, advanced OpenMP, and in some exposure to other programming models and languages. And then in some cases, we'll just give you a glimpse of what's available so that, maybe 3 years from now when you're facing having to do something of that type, at least you might remember there already is a project or some software that does that. And so maybe you won't reinvent the wheel. I mean, maybe you'll invent a better wheel, but in many cases, you at least want to know what wheels have been invented. Now, we'll be doing a fair amount of hands-on. But let me tell you a little bit about the official definition of the Department of Energy Leadership Computing Facility. It's formally one facility with 2 centers, one at Argonne National Laboratory and one at Oak Ridge National Laboratory, which is just outside of Knoxville in Tennessee. And the idea, and this was founded in 2004 by an act of Congress. So there's a law that says the Department of Energy shall have such a facility, and its goal will be to provide access for open research, not classified, to people around the world, to systems that are 10 to 100 times more powerful than you would normally have access to. And since we want people to be able to do things they couldn't do elsewhere, relatively small number of projects is given time on these systems at any one time. Because if we gave 10,000 people an account to do projects on Mira, for example, it would in practice not really be a big computer anymore because you'd be sharing with so many other people, you'd only get a little bit of time. The big allocations these days are 200, 300 million core hours per year per project. Anything under 50 million core hours per year per project, you can get, but you don't get that with the big award programs. It's considered to be too small if it's less than 50 million. Now, in addition to the big computers, of course, we have some smaller computers we'll talk about in a minute, but also we have a lot of people to help the projects that get time on it. So at Argonne, we have a team of computational scientists and engineers of about 15 of them that we allocate. Each typically has about 3 projects to work with. And so they help the project because they understand the domain, so for example, material science. And they also know our facility very well and how to use it. And so they serve as a bridge. So we call them catalysts. Oak Ridge has a similar set of people. They call them liaisons. We also have performance engineers who specialize in getting the most performance out of your program. And so they can be paired up with a project to help that way. Ray Loy, who will be talking after me, is, for example, one of the performance engineers. A little detail on the systems. Here we have an IBM Blue Gene Q called Mira. It has 49,000 nodes, each with 16 cores, and so you end up with about 750,000 cores. Now, each core has 4 hardware threads, so at the hardware level, it's about 3 million concurrent pieces of hardware that can be doing work for you. Peak performance is 10 petaflops. The Oak Ridge system is a different architecture, and that's also by design. We want to keep 2 architectures, the different architectures at the 2 facility centers. It's a Cray with AMD Opteron cores, 16 cores per CPU, but per node rather. So a total of about 300,000 cores. But then each node also has a GPU, an NVIDIA Kepler. And so the peak speed is 27 petaflops, 90% of which is from the GPUs. So it's a different architecture. And at any large center, of course, you don't have just a big machine. So here we have Mira. I've already told you that much. But then Vesta that you'll be using heavily, which is also a Blue Gene Cube, but it's instead of having 2 racks, as we call these, each with 1,024 nodes, instead of having 48 racks, there's only 2 racks for that. Cetus has 4 racks. And then we have a visualization cluster, which is a Cray CS, which it has Intel processors and NVIDIA GPUs. And then a lot of storage, 28 petabytes. Now that's today. In addition to the 2 leadership computing facilities, the DOE also funds a system at NERSC, which is at Lawrence Berkeley Laboratory in Berkeley, California. NERSC is the National Energy Research Computing Center. This gives you a glimpse at what's coming up in the next several years, starting in 2016 at NERSC, and here at Argonne we'll get a new system, and then a much bigger system in 2018-19, as well as at Oak Ridge. So the progression is, in terms of petaflops, the new Oak Ridge system will go from 27 to 150 petaflops. Ours will go from 10 to 180 petaflops, but with intermediate one of only 8.5. And this has a lot more detail that you can read at your leisure. But just looking at Aurora, which will be the 180 or so petaflop system we'll be getting, it's similar to Mira, even though it's no longer an IBM system, it's not a Blue Gene. But how is it similar? Well, it's homogeneous. Instead of having CPUs and GPUs, it's all CPUs and cores. It's many core, so each node will have a much larger set of cores than 16. And each core will again have 4 hardware threads, so that's the same. And they'll have SIMD units that are a little bit different. It is self-hosted and water-cooled. So it'll be 18 times faster, but notice that the peak power will only be 2.7 times as much. And that's important because one of the pacing items for the big systems these days is how much electricity does it take. So if you were to build an exascale system, 10 to the 18th today, with today's components, you would just about need a whole generating plant, a gigawatt or so. And since electricity costs about $1 million a megawatt a year, a gigawatt would be $1 billion a year just for power. And that's a lot of money. So we are pressing the companies that build these systems to be much more power efficient. And you can see they're succeeding. That's a big increase, factor of 6, right? More than 6. Now, because that system, Aurora, won't be delivered until around 2018, it's 3 years from now, we decided that we would get a small, only 8.5 or 8.3 petaflops, but with a very similar architecture to what Aurora will be. And so we'll be able to start moving our users and our applications to this architecture because it is different. It's the Intel x86, which of course will be good because there are a lot more of those systems in the world than there are Blue Gene Qs. Right? And so we'll be getting that, should be delivered just about a year from now, Theta will be. As you may know already, but just to remind you, we organized this training program around 7 major tracks. I felt you'd want to get pretty deep information about architecture and especially how to use the architectural features, but much of it relating to how you would make use of architectural features, not just architecture for its own sake. Then, how do you program these systems is a big deal, and there are several programming models and programming languages. So we'll be spending basically 3 days on programming models and languages. So it'll be Tuesday through Thursday. Numerical algorithms and software, libraries are very important, and so we'll have a day and a half on overviews of those with hands-on exercises as well. And then next week, Monday and Tuesday, will be community codes and software engineering with an emphasis on performance portability. Now, portability is important because major codes usually have a lifetime of decades, but individual computers typically have a lifetime of 4 years, 5 years. And so even if you stick to the same manufacturer, let's say Cray, over the last 20 years, there have been major differences in what a Cray computer looks like. So portability is important for these major codes. It doesn't have to be a major code for any code. And you may want to switch between using the Argonne system, which is homogeneous many-core, to the Oak Ridge system, which is heterogeneous with lots of GPUs, and still get good performance without having to rewrite it from scratch. Well, the truth is nobody has the right recipe to do that, but we're starting to figure out. And so on Monday and Tuesday, part of what you'll be learning about is some approaches that work at least part way. Toolkits and frameworks, believe it or not, there are parallel debuggers that do a reasonable job of helping you debug even with many thousands of cores. And so we'll tell you about some of those. Also, tools that help you determine where your bottlenecks are and therefore be able to eliminate them or reduce them and get much better performance. So that's what that will be. And visualization and data analysis, I mentioned before. And then Thursday, a full day on data-intensive computing and I/O. And in my experience, many scientific applications, you may not think of them as being data-intensive, but many in fact are. You're having to maybe read big input files, often generate very large files. One of our cosmology applications, for example, generated 2 petabytes in just 2 weeks running on Mira 3 years ago. That's a lot of data just for one application. They then generated 4 more, so now they've got 6 petabytes. They need to analyze it, so that's data intensive, even though cosmology is not related to experimental data, at least that simulation was not. So I want to thank and make you aware of that the Department of Energy Office of Advanced Scientific Computing Research, which is just part of the Department of Energy Office of Science, has provided the funding for this program. We got 3 years of funding 3 years ago, so this is the 3rd time we're offering this. And I have a tentative promise to fund this for 3 additional years. So if you know colleagues who, after you've gone through this, you would like to recommend it to, we do expect to offer it again next year. Now, we'll be giving you a chance to evaluate different parts of the program. And please take the time to do that. Evaluations for each of the tracks, like architecture, programming models, numerical libraries, and so on. That's a track, each of those. The overall program. And, of course, you can also talk to us as well. So thank you for taking a couple of weeks of your summer. I hope you enjoy it and you find it useful.